Okay, class. Today we are going to start to talk about chapter 7, energy principle. Okay, so conservation of energy for fluid systems start with this equation. So the change of energy in the system, dE over dt, will be equal to Q minus W dot. What is Q and W dot? The heat transfer, right? Q is heat transfer rate, Q dot. W dot is the work, right? So by convention, heat transfer into the system is positive, W is negative, work going out of the system. Okay, so the change of the Q minus Q dot minus W dot will be equals to it's the total energy change in the control volume plus the energy goes in and out of the control surface, just like conservation mass and the momentum. Okay, this is actually called Reynolds transport theorem. That's for fluid mechanics only, right? So this is rho dV integration on the CV. That's the total of energy in the control volume. Okay, energy times volume, right? Then this is rho VdA, it's the mass flow rate, right? So the energy flux goes in and out of the control surfaces. So the conservation energy in fluid mechanics, that's also we consider it on the control volume, right? So the summation of these two terms will be equals to the result, either heat transfer or work. Okay. So if we move, make a little bit modification for the work, we have flow work and the shaft work, right? We keep the shaft work and we move the flow work to the right hand side. Okay. So instead of U internal energy, we have an enthalpy H in the flux. Okay. This term. Okay, by the way, the three components in the parentheses for the energy, half V square is the rate of the kinetic energy, GZ the potential energy, U is the internal energy. And I'm out of letter, that's why I use U. It's not U velocity, okay? This is internal energy. So this is the three type of energies, right? It's total energy. So, but if we move the flow work to the right hand side, it become enthalpy here in the flux term. Energy go in and out the control volume. That will be H instead of U, right? The total energy inside the control volume is still U, okay? So the detailed derivation will be in the textbook. You can read it, okay? So let's say that if there's a special case, steady state plus uniform flow, as every conservation law before, we'll always look at the steady state and the uniform velocity, right? So if it's a steady state, that means this d over dt term is gone, okay? So you have only the energy in and out of the control surface term left, okay? So Q minus Ws shaft work, right? Q is heat transfer, Q dot, Ws dot is shaft work. It will be equals to energy half V square plus Gz plus H, it's enthalpy, times mass flow rate out minus half V square GZH in the inlet times mass flow rate in. Okay, similar term, similar form, like the other conservation laws. The conservation momentum is mass flow rate dot times velocity, right? Here it times the energy. So energy out minus energy in equals to heat transfer and work. In momentum is mass flow rate times velocity, right? Momentum out minus momentum in equals to the force. Here energy is in the form of heat transfer and the work. Okay. So this is the general equation, right? That we're interested in the pipe flow, okay? Later on, chapter 10 is totally pipe. flow, pipings. That's one of the focus in this class, pipe. So we want to look at the energy equation for the steady state fluid in a pipe. Okay, in a piping system, we can separate the shaft work into two major components, turbine and the pump. Okay, turbine and the pump. So shaft work equals to turbine and minus the pump. Pump is going into the system, and turbine is the energy, the work you receive, okay, from the system, right? You obtain from the system. Okay. So the equation is like this. Okay, I skipped some of the derivations. Okay, it's from that equation we will derive it into this. We replaced the enthalpy, okay, by velocity and the pressure. Okay, remember the reason we have enthalpy is the flow work, right? It's because of the flow work. Flow work is from the pressure, flow pressure. Okay, so the shaft work, we have two parts, right? WP and the WT, okay? So WP is because of the sign, WP is in the left-hand side and WT is in the right-hand side, okay? So we divided by m dot g for every term, okay, in this equation. We divided by the mass flow rate, okay? Seems in the pipe flow, because of the conservation of mass, your mass flow rate is the same, right? It's constant. Your mass flow rate in and the mass flow rate out has to be the same. Incompressible fluid in a pipe, okay, because of that. So m dot, we just have m dot mass flow rate everywhere, right? So we can divide by mass flow rate and g for every term. It becomes this. Okay, so the two work, WP and WT divided by m dot g become the heads. Okay, one is a pump head, one is a turbine head. All right, this is the head form. The equation, every term is a head. Okay, I want to mention the last term. Last term is the loss. Okay, if we put internal energy change and the heat transfer together, okay, become a term. That term is called loss. The loss is always positive. Okay, the loss is always positive. Well, why that? Look at the expression. Well, if your system is adiabatic, then no heat transfer. Okay, if you have an adiabatic system, then your internal energy will always increase. U2 will be greater than U1, right? Okay, so if Q is 0, adiabatic insulated system, you don't have heat transfer, then internal energy increases. So this term is positive. So if you allow heat transfer for the system, then the internal energy doesn't change. U2 minus U1 doesn't change, it's 0. Then you have heat transfer out, it's negative, right? Negative become positive. Okay, so it will always be positive. So there will always be a loss, positive loss in the system. Okay, this is the pipe equation. Notice here there is an alpha. Okay, what is alpha? Alpha in front of the kinetic energy term, right? V squared over 2g. Velocity head, you have alpha in front of it. Alpha is called kinetic energy correction factor. Notice in this actually equation, okay, you have integration. Okay, we only can specify uniform velocity, then you become like this. But what if the velocity is not uniform? It's not exactly. You can because you see velocity term, you have v squared times v, right? Vq. You can separate the mass flow rate with the energy term for the velocity. So you cannot get rid of the integration. So what we do is we specify we assume it's uniform, and we specify a coefficient if it's not uniform. So this kinetic energy correction factor, if it's alpha equal to 1, that means it's a uniform flow. If it's uniform flow, we can get rid of the integration sign, right? But if it's not uniform, if it's a laminar flow, alpha is 2. Okay, so we have a correction factor. That's the engineering engineering process, right? Engineering way. So we just assume we can take the integration out and by multiplying a coefficient. Okay. Notice that one thing I want to emphasize: if it's a turbulent flow, the turbulent flow, the velocity distribution inside the pipe is rather uniform. Okay, although in every point it fluctuates, it changes, but the mean value, mean velocity profile in the pipe is close to uniform. Okay, we're not talking about instantaneous velocity profile. It's a mean velocity profile is similar to uniform. So 95% of the flow you see in the real practical application is turbulent flow. So alpha is actually close to 1. Okay, if you take the mean velocity for the calculation. So based on that, let's say for the turbulent flow, so we'll get rid of alpha. Alpha is close to 1, so we'll get rid of it. The equation become this for the pipings, for the pipe flow, turbulent pipe flow. Okay, P1 over gamma plus Z1 plus V1 squared over 2G plus pump head equals to P2 over gamma plus Z2 plus V2 squared over 2G plus HT, turbine head, plus the loss, head loss. Okay, this is an equation that looks very close to Bernoulli equation. Okay, so notice that this, I skipped a lot of derivations. Okay, it's in the textbook. Please read it. Okay, but at the end you have actually two. This is the general conservation energy equation in the flow system. Okay, and this one look very close to Bernoulli equation. It's the conservation energy equation in the pipe, in the incompressible pipe flow. Okay, for the incompressible pipe flow. Okay, most of your applications, homeworks, we're actually using this equation. Okay, it's a pipe flow that we are interested for the conservation energy principle. Okay, couple of things I want to add before we talk about some examples. Okay, so the powers, right? So the power equation for the pump and turbine. So in the equation we use pump head and turbine head. But what if we want to calculate the total power required for the pump, or the total power we can receive from the turbine? This is the equation. Remember previously we W dot the work divided by mass flow rate and G to get the pump head and turbine head. Now we do opposite, right? So the pump head equals mass flow rate times G times the pump head, right? If you rearrange it, if you transform it, it will be Q flow rate, volumetric flow rate times delta P. If we want to use delta P, right? Then or you can say Q times gamma. Mass flow rate is Q volumetric flow rate times rho. Rho times G is gamma. So Q times gamma times the pump head. Okay, is also the power, pump power. Same thing for the turbine. Volumetric flow rate times gamma times turbine head. You can calculate the power of the turbine. Okay. Well, what does this two power means? You know, it's when you put a pump in the system, you're adding energy to the system, right? You're adding work, adding power to the system. So that's the power that added to the system from the pump. Okay. For the turbine power, if you put a turbine there, you receive energy from the system. You take energy away from the system, right? That's the power of turbine that you can take from the fluid system. That's kind of a certain energy. That's the amount of energy you can take from the fluid piping system. For the pump power, that's the energy you needed to add it to the flow system. Okay. Turbine is what the energy you can get from the system. Okay, sometimes we talk about efficiencies, right? So efficiency from 0 to 1, you know, turbine and the pump, both are mechanical device. They have losses, right? itself, it's not the flow loss. It's the loss from the mechanical system of the turbine and the pipe. So when you run it, you have a efficiency from 0 to 1, right? Efficiency. So for the pump, the flow system requires a certain amount of power, right? Let's say W dot P. That's what the system required. You have to pump certain amount of power in there. But if you look at your electricity bill, the power you pay for it actually is bigger than the flow system needed. Okay, that's why your W dot P should divide by the efficiency eta to have the actual power needed. Okay, I said W dot P actual. Your actual power needed will be bigger than the power needed by the flow system, right? You have losses there. But for the turbine, how much actual power you actually get from the system is actually less than the power immediately from the equation, right? From the equation, how much power you can get, because then the turbine you have losses. The actual electricity or whatever power form you get from the turbine is less than the theoretical ideal power you get it from the system. So here W dot T should times multiply by the efficiency. You have the actual power gain. Okay? Be careful, don't confuse with that. These two etas. One is divide, one is multiply. So I want to add a couple discussion here. The energy equation and the Bernoulli equation. Look at the energy equation in the pipe. They look similar to the Bernoulli equation, but it's not really Bernoulli equation. You know it, right? It's because look at this equation here. It looks like a Bernoulli equation, very similar. Pressure head, elevation head, velocity head, but they have three terms there: pump head, and then three additional terms: pump head and the turbine head and the head loss. Okay, so the pump head and the turbine head is from the energy equation, from the derivation for the viscous fluid. Okay, because the viscous effect. But Bernoulli equation, remember the derivation. There's no viscous effect included. Okay, it's really a steady state incompressible inviscid fluid for the Bernoulli. But energy equation is viscous, and this is for the pipe flow, that equation. So they're totally different equation, although they look similar. So in industry, people always call this Bernoulli equation, but in your heart, you know they are really not. They're really not the same. They're derived from totally different starting point, and they serve for different purposes. Okay, and the Bernoulli equation starts from the second law, right? From F equal to ma, right? From the streamline, okay? From the momentum equation. But energy equation is from the conservation energy, right? So the starting point is so different, okay? And it happened to look similar, but they are really not the same, okay? They are really totally two different equations, okay? And be careful, again, when we look at this equation, be careful. Pump head is in the left-hand side of the equation, and the turbine head is in the right-hand side of the equation. Don't switch it, okay? Loss is also in the right-hand side of the equation. So what does that mean? Okay, 1 and 2 here in the equation. 1 is the beginning of the pipe, at the inlet. 2 is at the outlet, right? The left-hand side of the equation talk about the total energy you have in this system. You know, you have initial energy, P1, Z1, V1, right? Initial energies. And the pump head is the energy added to the system. So that's the total amount of energy you have, okay, in the system. And the right-hand side of the equation, we talk about the total amount of energy, how do they distribute? Okay, where does those energy goes eventually? So part of the energy goes to the outlet, right? At the outlet, you still have pressure, elevation, and velocity. So they have still some energy left, but some of the energy goes to the turbine. You take some of the energy away, okay? Some of the energy goes to the loss, head loss. So the total initial energy, that amount, it goes to these components. It's outlet, you still have something left. Turbine, you take some energy out of the system, and the loss, then some energy lost forever. Okay, so don't switch the side for the pump head and turbine head. Pump head has to be in the left. That's adding to the energy added to the system. Turbine head is in the right, and the loss is also in the right. Okay, so this is the theory of the chapter 7, conservation of energy. I will present you some examples in the next videos.